All right, questions? All right, so we're studying the primes and some properties of them and factoring with the fundamental theorem of arithmetic. The idea that if P, if n is greater than or equal to 2, then n is prime, or can be written as a unique product of primes in non-decreasing order. So we have this particular theorem that all things are either prime or a product of primes. We really could say everything's a product of primes if you allow a prime by itself to be a product. You say, oh, it's a prime all alone. What's it multiplying? Nothing. No, it's a product. So really what we're talking about is the primes in the composites. If it's a composite, all composites are actually inside of them. What builds them up is a unique product of primes as long as you write them in non-decreasing order. So finding where the primes are would be important. Last time we stopped on the fact that, well, okay, how many primes are there? When we saw the sieve of Eratosthenes, you start crossing things out. Under the sieve, you start off at 2, then all the evens are gone, and 3, then all multiples of 3 are gone, then 5, and then all multiples of 5 are gone. Do you eventually cross everything out? And the theorem that we could get out of that would be there are infinitely many primes. The idea behind this proof, or the proof itself, would be simply flipped around. Let's say somebody said that I believe that, assume there are finite primes. Right? So let's say somebody said, I just believe the opposite of what you just said. I believe that there's actually finite primes. Well, if you believe there's finite primes, the primes themselves have to be simply prime 1, prime 2, prime 3, up to prime n. Notice I'm not saying what the primes are. You know, people can try to put them in order, 2, 3, 5, 7. Right? I'm not any order or whatever. I'm just saying that there's just a finite number of them. All right, by the fundamental theorem, all numbers are either prime or a prime divides it, right? Because if it can be written as a product of primes, there's a prime that would divide it in a particular way. So if it's a composite, it has a prime divisor. All right. Well, I'm going to look at two numbers. Let's consider number 1, which is just simply going to be prime 1 times prime 2 times everything up to prime n. So people take this and say, oh, look, there's a large number of primes. It means it's a big number. Well, yeah, it's a big number. Is it bigger than all those primes? I don't know. I mean, yeah, you would assume to be so, but I'm not telling you what the numbers even are. All I know is it's just simply take all the primes that you say exist and multiply them. The second number that we're going to consider is take all the primes that exist, multiply them, and then just simply add 1. What's the next number? So I'm finding these two numbers. One number is take all your primes, multiply it, it's this. And the next is the next number. So we're taking two integers right beside each other. All right, now by the fundamental theorem of arithmetic, these things are either composite or they're prime. In particular, that first one's rather easy. It's a composite, right? I took all the primes and multiplied, so it's obviously a composite number. And so it's a composite. Now, not only is it a composite, I notice that any prime, let's call it P star, divides N1. What does it mean to divide? That means it's a factor of. For n1, are all of the primes a factor of this number? Yes. Now let's consider, so that's the first thing. Second thing is n2 is either prime or has a prime divisor. That's by the fundamental theorem, right? It has a bunch of primes that multiply uniquely to it. In other words, it's composite. It's either prime or composite. If it's composite, it has a prime divisor. All right. Obviously, it really doesn't matter if it's prime or it has a prime divisor. Something divides it that's prime. Let's really put both of those two together. Together, what this says is some prime must divide it. Either itself, if it's prime, or just some prime, if it was a composite. I don't care which. And let's say that, so some prime divides it. Let's call this some prime. Let's call it, I don't know, P. And that means that P divides N2. Where P represents some prime. I don't know what it is, don't really care. It exists. This is a non-constructive existence, right? Did I tell you which prime it was? No. Do I care what it is? No. I just know it exists. All right. If any prime divides N1, does that mean that P also divides N1? Everybody answer your head, yes. Since any prime divides N1, this special prime that divided N2 must also divide N1. So this little prime P must divide N1, and this prime must divide N2. If you have a number that divides two different numbers, what's our theorem? It divides any linear combination of those two, right? I could have 5 of the first and 4 of the second. I could have 2 of the first and negative 20 of the second. All right, any linear combination. Well, that would tell me that the prime must divide. I'm going to take 1 of the first and negative 1. Which way? No, I want to go the other way. I want negative 1 of the first and 1 of the second. Negative 1 of the first and 1 of N2. Because it'll divide any linear combination. All right, let's look at what those two numbers are. If I take 1 of N2 and negative 1 of N1 and I put those two together, what number comes out? 1. Oh, okay. Well, that just simply tells me that the prime must divide 1. What prime divides unity? What can divide unity? Nothing. It's unity, right? It cannot be divided. That's logically what? False. So what does that mean? It means that the primes can't be finite. The primes being finite, right? The primes being finite means that I could make two numbers based upon these finite primes, but that really says that since these numbers are either composite or prime, right? The first one is definitely composite. The second one's either prime or composite. It doesn't matter. Some prime divides it. So therefore, it has to divide their difference. It has to divide 1. Or that doesn't exist. That's impossible. Therefore, we're done. Your original assumption was wrong. There has to be an infinite number of primes. Now, the next question that we would have on this, and if you look at the book, I mean, they have this same idea going on. Notice people say things like, well, but, you know, I took this product plus 1, well, that has to be prime. And it's like, really? It always has to be prime? Because we could take things like, you know, we could say, well, 2 times, because I don't know which primes that you're calling primes are actually prime, right? You just said, I have a finite number of primes. Well, we can take finite numbers of things, add 1 to it, and get to a non-prime. Say, is 2 prime? Is 7 prime? And so those are the only primes you found. But what's 2 plus 7? 2 times 7 plus 1? 15. But then if we do enough work, is that a composite or is that actually a prime? And it's like, no, we're thinking of it wrong, right? A lot of people say, well, if we product, we get primes. What's nice about this particular proof, what are we talking about? Are we putting any restrictions on this list at all? No, we just say it's a list. And from your list, I make two new things from your list. And by understanding what it means for the fundamental theorem, we're going to get to this issue of you're going to have to be able to divide 1 for this to work, which can't happen. All right. So we know there's an infinite number. One of the things that we can also ask is, how rare are them? How rare are they? It seems like it's been a week now that my ability to speak has slowly gone down. It's bad enough, but it keeps getting worse. So we're going to develop a new function, and we're going to call this P of x is the prime counter. Obviously, this thing is an increasing function that goes up to infinity. What this does is it counts all primes up to the number that you're looking at. For example, pi of 3 is 2, because 2 and 3 are primes, and so pi of 4, well, that's also 2. Pi of 5, well, that one's 3, right? What it's doing is it's counting how many primes do you have up to this number. And so we could have things like, what would be pi, this prime counter of 10. How many primes are between 2 and 10? 2, 3, 5, 7. So the answer is 4, right? So what this function does is it just simply counts how many primes exist. This is obviously, it's going to be increasing. It's going to infinity. One of the questions is, well, how fast is it? What type of shape does this look like, right? It's a bunch of dots that are going to be going up. I know it goes up to infinity, but what shape does it have? And we have the following theorem, which would be the limit as x goes to infinity of this prime counter and the curve x over natural log of x. So if I would do this prime counter and then x over natural log of x, and I would look at these two curves, as we go to infinity, their ratio is 1. What this is telling us is, so for large x's, the counter can be approximated by x over natural log of x. Does that go into infinity? Calculus, what would we do with this? Well, take the limit as x goes to infinity of x over natural log of x. What's the limit of x? Infinity. It's a straight line. What's the natural log of x? Where does it go? Infinity. So type infinity over infinity, you would use the L'Hopital's rule. Take the derivative of the top, take the derivative of the bottom. What's the derivative of the top? 1. What's the derivative of the bottom? 1 over x. It flips, and so we would just have x. That is going where? Infinity, right? So its limit's infinity, right? It becomes unbounded. Natural log of x is growing unbounded, x is growing unbounded, but x grows faster than natural log of x. So this is growing very slowly, but it's growing. Not very slowly, but reasonably slowly. All right, so we would have things like, we could do an approximate. So for example, pi of 10 to the 10th. how many primes are there from 2 all the way to a 1 followed by 10 zeros? Which is what, 10 billion? Is that right? 1, 2, 3, 1, 2, 3, 1, 2, yeah. 9 is a billion, so 10. So this is 10 billion. So from 2 to 10 billion, how many primes exist? Well, we would approximate it. What is this? 10 to the 10th divided by the natural log of 10 to the 10th. But that's equal to 10 to the 10th divided by 10 natural log of 10. One of those 10s cancel. And so this is 10 to the 9th divided by the natural log of 10. What's the natural log of 10 about? Natural log is log base who? E, right? So we're log base E. E is about what int? 3-ish, right? All right, what's 3 squared? 9. This is about 2. Is everybody okay with that? Natural log of 10, 2-ish. So what am I doing? What is 10 to the 9th? A billion divided by 2. What's this ballpark? We're just approximating. 10 to the 10th is approximately what? 1/2 billion. Think about that for a second. From 2 to 10 billion, how many primes are there in that entire list? About 1/2 billion primes. All right, this automatically leads to an issue of why is factoring expensive? The reason why factoring is expensive is because if 2 does not divide something, what does it tell you about the rest of your primes to check? Nothing. If you're going to factor, what do? You try 2, you try 3, you try 5, you try 7, you try 11. If the answer is no, 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 does it tell you anything about 13? No, you have to try 13. You have to try 17. You have to try... The thing is, if you're going to truly factor something, the only way to check it is to check all of the primes. So if I was factoring numbers of about 10 billion squared, right? If I'm factoring numbers of about 10 billion squared, that theorem tells me that I have to check which primes? Between 2 and 10 billion. But that leaves you how many primes to check? About 1/2 billion things to check. And they all must be checked. Because the only way to guarantee that you can't factor is that you actually check them all. That's the only way you can actually check a prime. That's a lot of primes to check. Now, if you would look at it and say, well, that doesn't seem to be that many. Well, you start to look at some time, like how long would it take you to actually do this? To do 1/2 billion prime checks. Well, you'd have to find 1/2 billion primes first, and then you would have to check them all. And so computationally, this is going to cost you money. Now, it wouldn't be too bad. Like, what if we had like an entire cluster of machines? And if you wanted to make it take it large, if you wanted to take a larger amount of time, then just simply let's just double the size. This increases non-polynomial. So. One of the things that we could talk about, the probability. Probability itself of an event is always the same thing. It's the metric of event divided by the metric of the universe of discourse, the thing that you're talking about. If you're going to say probability that something occurs, so we would have things like examples of this. When I'm talking about the metric, it doesn't necessarily have to mean counting. So we would have problems like, what's the probability of rolling an even number on a 6-sided die? Well, how many ways could you roll an even number? 3. How many faces are on a 6-sided die? So the probability would be 3/6. Right? What if I had a 7-sided die? It would still be 3, right? What if I said, what's the probability of picking an integer between -2 and 5 of all integers between -5 and 20? If I would say, what probability of int from -2 to 5 of -5 to 20? How many integers are from -2 to 5? There's 8 of them, right? There would actually be 8 of them, right? And then how many integers from -5 to 20? What if I asked you for the probability of a real from -2 to 5 of -5 to 20? Here's an interesting question. The integers were objects. I could actually count them. Can you count the reals? No. So what metric would we use? If I tried to, one of the ways that you measure things is there's 2 bad measures, usually, which is 0 if you get the wrong size, right? And so sometimes, like, if you know it exists, it has a value, but you get an answer of 0, that tells you that you're picking the wrong metric. If you get infinity, that's the wrong metric. For a line, and you try to count dots on a line and you get infinity, that says you're using the wrong dimension, 0th dimension. So what would be the next dimension up? 1. So what would be my other metric? Length. What's the length of reals from -2 to 5? There we get 7, right? That's the length of that line. In other words, this thing has gone this. Here is -2, here is 5, and I calculate a length. That is 7 wide. But from -5 to 20, how wide is that? 25. And so length, this is 7/25. It's a different probability because I use the metric of length. This idea is used for lots of things. When we do, like you can calculate the area of a pond by just simply throwing rocks. What you would do is you would just simply create a big square around the pond that you know is a fixed size. That's your universe of discourse. And then you randomly throw rocks over your shoulder that could randomly land anywhere in the entire square. And you count splashes. Oh, and if you throw enough of them, you get a reasonable approximation. And you say, oh, look, there's 25% slashes. I hear 25% splashes, right? Which would tell you what about the area? It has to be 20% of the entire thing. Why? Because probability. Exactly. We could do probabilities with areas. We can do probabilities with length. We can do probabilities with volumes. We can do probabilities with dimension 0, which is cardinalities, count. Now, most of the times you do statistics, we stay in counting. You don't have to stay in counting. You can move into other metrics, length, volume, hypervolumes, whatever you want. All right. What's the point of this? Well, what's the probability that x is a prime? All right. Probability of x it's a prime. How many primes are there between 2 and x? Remember, what are we going to do? We're going to count the event, primeness. So that would be that pi function counts that. That tells me how many primes there are. How many total numbers are there? X. Okay, but what is this approximated by? What is pi of x approximated by? And that is what? So that's the probability that you've actually randomly picked a prime, roughly. So if I picked a number, and what would we do? We would simply, here's one approximate. Pick a large odd. Instead of sitting here saying that I'm actually going to check to see if it's a prime, what's the probability it's a prime? What's the percentage chance that this large odd number is a prime? 1 over the natural log of x, right? And so you can do that. You just simply say things like, I'm going to pick a really, really, really large odd number. It's impossible for me to actually generate enough primes to test it, but I could actually give you a probabilistic, say, I think it might be a prime, and I'm 98% sure because it's, we would simply go through there, or you would go through different things, and that's what's the odds of it being a prime. And so those are the sorts of stuff that we do. And for very large prime generators, what you do is you generate a large odd number with certain techniques, and then you have to, a lot of times you can't truly prove it's prime. You have to throw stats at it to make it a better chance of being prime. And as you tell, what is the probability to do as x goes to infinity? It's going to 0, right? The larger and larger you take, the fewer and fewer primes there are. There's still a lot of them, but they become rarer as you go. All right, what's some stuff that we can do with prime factorizations? We'll look at the GCD and the LCM. Greatest common divisor, least common multiple. The greatest common divisor is find the largest number at or below your two numbers that divides both of them. And so what we're looking at here is if you have A and B on a number line, right? So the GCD is, so here's 2, here's 3, etc., and there's A and B. The GCD is largest number, say G, that divides A and G divides B. So that's the GCD. What's the biggest number below this? And actually we ought to go, sorry, forgot, 1. 1 divides everything too. What's the largest number below these guys, the guys furthest to the right, that is going to both divide A and divide B? On the other hand, the LCM goes up, and the LCM is going to be the smallest number above that A divides that LCM and B divides the LCM. These two numbers below are now numbers of, I want to divide up some bigger numbers. Obviously there's an easy one, A times B, right? A divides A times B, B divides A times B. That doesn't necessarily, that's a common multiple, right? But that doesn't necessarily mean it's the smallest. I'm going to look for the smallest number that both A and B divide. The way you find these is through the prime factorizations. So you would say, if A is equal to, say, prime 1 to a power, prime 2 to a power, prime n to a power, and B is equal to prime 1 to a power, prime 2 to a power, prime n to a power. And we're going to use the same primes. So I've done a prime factorization. So say, for example, 12 is equal to 2 squared times 3, and say 15 is equal to 3 to the 1 times 5 to the 1. If I would look at this, and I'm going to look for the GCD or the LCM, what I'm really going to say is, what are all the primes that I see between the two numbers? 2, 3, and 5. So I would say that this is 2 squared times 3 to the 1 times 5 to the 0. And 15 is 2 to the 0 times 3 to the 1 times 5 to the 1, right? So I make it so that they all have the same primes. So we prime factor both of them, and then we just simply write down all the primes that we have in both. And we write them in, obviously, non-decreasing order. That's what I'm talking about. So we prime factorize in the following way. And then what we have that's nice is the GCD between the two numbers is simply take all of the primes and take, what's the minimal number of occurrences? And the LCM does the exact opposite. what is the maximal number of occurrences? Whoops. It's a B2. That, though, is a B1. So, for example, again, what would be the GCD of 12 and 15? Write your primes. What is the minimal number of 2's that you see between your two numbers? 0. 15 has none of them. What is the minimal number of 1's between the two numbers? What is the minimal number of 5's? And so the answer is simply 3. 3 is the biggest number that you have that divides both 12 and 15. The LCM of 12 and 15 says take your primes, 2, 3, and 5, but take the maximal number. What's the most occurrences of 2? 2 of them. What is the most occurrences of 3? 1. What's the most occurrences of 5? 4 times 15 is 2 times 30, 60. That is the smallest of the numbers that both 12 and 15 actually divide. It's obviously smaller than 12 times 15. I know 12 times 15 works, but I also say, no, what's the smallest of these? Well, 60. What do you notice? What's 3 times 60? It's 180. What is 12 times 15? 180. Right? And that's always going to be true. It always ends up being that A times B is equal to the GCD of A and B times the LCM of A and B. Why is that? Well, if you would look at it this way, you would just simply say, okay, wait. The GCD takes the minimum of occurrences, yes. And then you take the maximum of occurrences, yeah. Well, didn't you just take all of them? Because how many occurrences are there? There's 2. So if you take the minimal and the maximal, you've actually taken what? Both of them. You either took the primes from the one number, and then the other one goes to the primes to the other number. So this basically resorts all those primes. We take the minimums to one side, the maximums to the other side, it just rearranges them. Well, all the primes are still here. Right? A times B is just take all the primes that you see and multiply them for both. So it's just a rearrangement. And then our little example here, that 12 times 15 is 180, which is also 3 times 60, which is 180. We're okay with that? All right. Nice and all that we can find GCDs. There's a nice little feature of this. How many are familiar with your whole prime factorization tree, finding the GCD and the LCM? It's like you sit there and say, why did I have to do all that? That seems to be, middle school work. Factoring, what's my greatest common divisor, what's my least common multiple, because I needed to find those sorts of things on my divisors to add fractions and different, common denominators was similar to common divisors and common multiples. So we did this sort of work before. One of the questions would be why. And the first thing would be if you would have the GCD of A and B are 1. If the GCD of A and B are 1, what you're saying is the largest number that divides them both is 1, which really would say that they have no common factors. Outside of 1, because everybody has a common factor of 1. Nothing else can divide both of them. So if I do all the prime factorizations, in other words, no common primes. They have no common primes between the two of them. And if that's true, we'll go ahead and call these relatively prime. All right, being relatively prime will be important here when we finally are able to talk about when do things have a modulus or a congruency by div modulo m inverse. Is there an int times a number under mod m that would give you back? Remember that whole class of ones that we have? 1 is congruent to 1 plus m, or 1 plus 2m, or 1 minus m, right? All of those numbers are the same as a 1. And one of the questions would be, could I take any int and multiply it by something and get one of those numbers? In other words, I need to have an inverse. Do inverses exist? If 1 is the identity, or the class of ones under congruency is the identity, does any number have an inverse? So we had examples of that, and relatively prime will be important for that. And this will come from two theorems. The first one is that if you can go ahead and write A equals BQ plus R, so you can do the division algorithm, this idea of sharing algorithm. A is bigger than B, and you can say, okay, A is how many B's plus R? We would work this entire problem out. One thing that you can notice would be that the GCD of A and B is going to be the GCD of B and R. This forms what's called Euclid's algorithm. This allows you to do a reduction problem. All right, if A is bigger than B, I'm taking the GCD of some large numbers. Now before, if I would have to do prime factorization, but factoring costs you time and money, would there be a better way to do that? Well, if I did the sharing algorithm, what do I notice about the sizes of B and R? Well, R is the remainder, right? R is always going to be between what and what? 0 and B minus 1, right? It's smaller. So I could go through a problem and say, okay, what's the GCD of 15 and 12? I already know what the answer is, right? It's 3. Well, Euclidean algorithm says, all right, fine. 15 is 112 plus what left over? 3. So that tells me that the GCD of 15 and 12 is actually the GCD of 12 and 3. But how could I find the GCD of 12 and 3? Well, the GCD of 12 and 3 is 12 is 4 3s plus nothing left over. And so we would just simply continue this process to ask until we get to the question of what was the last remainder in its 3. So the Euclidean algorithm just simply goes, you take your two big numbers and you write it in the division algorithm, and you get your 12 and your remainder. All right, now I want to find the GCD of that. Let's just do the division algorithm. And we could go through a lot of these problems. You look through the book. You know, this was a two-step one. Some of them are down and down and down and down and down and down, right? And we keep going. One of the things that I can notice on a problem like this is, do another example of it. GCD of, say, 25 and 7. I already know what it is, but what is a GCD of 25 and 7? So it's going to be 25 is equal to how many 7s? 3 7s with what left over? 4. And so what I'm looking at now is the GCD of 7 and the remainder. But what is that? Well, 7 is equal to how many 4s? 1 4 with 3 left over. So now I've gone to the GCD of 4 and 3. But that is 4 is 1, 3 plus 1, right? So now I've gone down to the GCD of 3 and 1. But 3 is simply 3 ones plus 0, therefore the number above is my answer. It's just simply 1. So I'd call them relatively prime. Is 25 a prime? No. But what are its prime factors? 5 and 5. What are the prime factors of 7? 7, right? Do they share any common primes? No, they're relatively prime. All right, one of the nice features is, let's look at this one for a second. This 1 ends up being the GCD of those two numbers. So that goes and says, all right, let's look at this line for a second. I notice that the GCD, I have the answer. It's 25 and 7 is 1. What would happen if I threw this entire thing in reverse for a second? So that tells me that GCD but 1 is equal to 4 minus 1, 3. Now what I'm going to do is I'm going to go backwards and see what happens. But what's 3? 3 is 7 minus 1, 4, right? So that tells me that my 1 is equal to 4 minus 1, 3, but 3 is 7 minus a 4. How many 4s do you see? Two 4s, right? Do you see 2 4s? So that tells me 1 is actually 2 4s minus 1 7. But what's a 4? A 25 minus 3 7s. And I still have my minus 1 7. Is everybody okay with that? So, what have I shown? 1 is equal to, how many 25s do you see? 2 25s. And then how many 7s? -6, -1, -7, 7s. Kind of look at that and you ask, well, why in the world would you care to do this? Well, this forms what's called Bezout's theorem. Bezout's theorem says that you can always write a GCD as something times A plus something times B. Is that what I did? I showed that the GCD of 25 and 7 is 1. But what is it? It's 2 25s and -7 7s. Because 50 minus 49 is 1. All right, now, which most students all say, who cares? Right? Why does this seem to be important to you? Well, this actually gives me the idea of congruency. If I would look at this and say things like, all right, because 1 is equal to 2 times 25 plus a -7 times 7, right? (25) and 7 are relatively prime. What would happen if I did a mod 7 to both sides of this thing? What if I did this entire thing and just simply say, I'm going to take mod 7. The left-hand side is still what? 1. What's my right-hand side? Well, this is still going to be 2 times 25 That'll be mod 7, right? But what is this? What's that mod 7? It's 0. It's a multiple of 7, right? Its remainder is 0. So what did I just show 2 and 25 are under modulo 7? 2 times 25 will always spit out a 1 under modulo 27. So what would you say 2 and 25 are mod 7? They're inverses. So this gives us two things to check to see if, how does a number have an inverse? It actually gives us, not only do I have to look, I need to have the GCD needs to be 1, and 2, it gives me a process. Euclid's algorithm, back thrown in reverse, will tell us the number right in front of it. It's S to T, right? S to A, T to B. The number in front will be its inverse. So this gives us a way besides doing it the hard way. So if I want to have a, does, say, A under congruent mod M have an inverse? Step 1, GCD of A and M must be 1. Must have this. And then the answer will be yes. If the modulus in your number are relatively prime, the answer will be yes. A will have an inverse. And then what do we have to do? Use Bazelt's identity to find the number in front of it. So that gives us the ability to find inverses. And the other thing that comes along with this is the following theorem, which is if P is prime, if A times C is congruent under modulo M to B times C. The whole point of having an inverse was to get rid of C, right? I'd like to be able to remove C so that A is congruent to B. C can only be removed if the GCD of C and M is 1. What does that actually tell you? If the GCD between A and M is 1, C inverse exists. And because C's inverse exists, this tells us that we can just simply go ahead and wipe it out. Just remove it. Simplification is allowed. So we just go ahead and remove it. We have A is congruent to B. All right. The next thing we'll start moving on to is I would go back and kind of review using Euclid's algorithm a lot, because we're going to be using it a lot because we're going to move on to applications of number theory, with the primary application being cryptography. And we'll spend a couple of days on that. For attendance, where's it at? 4.329. All right, that's it.